welcome. I don't know anything about anything other than my show, so I'll just get into my show. So I just put a couple of questions up here to think about. You know, this is a small enough group that I think we can be reasonably interactive. So even the people at the far end there, which I see as mainly the analytic team. Well, you guys are sociable. Hi. You know, if you have any questions, comments, thoughts, you know, yell out, because I don't have any slides. Well, I have one slide. So my one slide is my answer to these questions, like what am I doing with deep learning? And I don't know how many of you saw this news, but we had a good week at Analytic. We're using deep learning to transform how medicine is practiced. And this week we announced our Series B, so we've now raised $15 million for that mission, and more importantly announced our first major site-wide integration, which is at a company called Capital, which is the largest radiology service provider, or actually the fastest growing radiology service provider in Australia. So it's been an exciting week because we now have access to, you know, tens of millions of patients of images. We now have access to hundreds of radiologists who are ready to start using our, you know, deep learning algorithms to help them with their work. This is kind of the first big step for us towards our goal, which is that every medical decision will hopefully one day be powered by insights from analytic algorithms or analytic software. We're starting in radiology because radiology has already been digitized for 20 years. It's kind of a lot of low-hanging fruit there. And also, of course, computer vision is something where deep learning is already superhuman performance in at least some areas. So it's a good place for us to start. I mentioned this partly to show off because I'm proud that we've got here, you know, but partly also because this is my kind of sample answer to these questions. For those of you that don't know, I was previously president of Kaggle. After I left Kaggle, I spent a year doing nothing but trying to answer these questions for myself. So I spent a year speaking to hundreds of industry leaders, scientists, politicians, you know, everybody basically. And what I would do, I had this standard kind of deep learning presentation, like 12 slides, a bit like the TED Talk I've got, which some of you have seen, where I basically said, here's what deep learning can do right now. What would it mean if you had access to that technology? And then they would, you know, almost always they would be like, shit, that would transform my entire industry. And so I spent, you know, a year trying to figure out, okay, well, what industry should we try and transform? And we decided, you know, in the end, medicine, because medicine, you know, there's 4 billion people in the world that don't have access to modern medical diagnostics, which is not okay, particularly in China and India. And then secondly, it's the world's largest industry, $8 trillion a year. Those places that don't have access to medicine, like China and India, that's where about half of new health IT spending will be coming from in the next 10 years, so it's also a huge financial opportunity. So that's what it looked like for me when I tried to answer these questions. And so I wanted to start here because the rest of the day is going to be, you know, tutorials about how to do shit with deep learning, right? So I kind of wanted to start with like, okay, well, what shit should you do? Or what's a way of thinking about what shit you should you do? So my starting point, I think, today then would be to say, well, what is deep learning really? My answer to that question is it's basically, that's way too big. It's basically linear algebra plus optimization. And those are two topics which are not rocket science. You can basically demonstrate all the pieces of deep learning in Excel. Not only can you, but I will do it right now. So here is Excel. the world's most popular functional programming language. Seriously, this is a totally pure functional programming language, and it's used by 500 million people around the world. So if you're interested in helping people use and understand deep learning, this is the best way to start, in my opinion, is in Excel. So here's some data I put together, some random numbers, and I then have AX plus B. So in this case, the AX plus B is going to be 30 plus 2 times B. Okay, so here's an independent variable, here's a dependent variable. How do we go about reverse engineering the 2 and the 30? So, here's the whole thing. So in Excel, I said, all right, here's just copying and pasting, here's our x's and here's our y's, right? And I said, well, let's start by assuming that the intercept is 1 and the slope is 1. All right, let's just assume that. So here we are, row 1. Row 1, data point number 1, input is 14, output is 58. If the intercept was 1 and the slope was 1, then we would be predicting 14 times 1 plus 1 equals 15. All right, can everyone see that okay? Do you want me to zoom in a bit? I'll zoom in a bit. If you can't see it, just raise your hand. So how bad was that prediction? Well, it should have been 58. We predicted 15, so the error squared is 1849. All right. Well, that's not very good. How do we make it a little bit better? We make it a little bit better by changing the intercept and the slope to be a little bit closer to what they should be. We know what they should be because we can take the derivative with respect to those two things. We can do it 2 ways. The first is that we can use the chain rule, this is backpropagation, right? So step number 1 is that the error is basically ax plus b minus y squared. The derivative of that with respect to ax plus b minus y is just 2ax plus b minus y. So the first piece of the chain rule then will be the derivative with respect to b. Well, what's the derivative of b with respect to the inputs? It's 1. So the derivative, here we've got derivative of e with respect to b is equal to 1 times my calculation. And then the derivative with respect to a is, well, ax, the derivative of that with respect to a is just x. So we've got x times 2ax plus b minus y. So that's backpropagation. The chain rule, that's all backpropagation is, it's the chain rule. So we can use Excel to calculate our derivatives. Here's our derivative number 1, 2 times all that. Here's our derivative with respect to a. And now we're done. So now that we've got the derivatives, we can change the slope in the intercept to be a little bit better by simply subtracting the derivative from the original slope. So here it is, the original slope minus the derivative times something. What's this something? This is the learning rate, right? In other words, this is just one example, right? So this is not the truth of the matter in every case. So we're just going to go a small step at each time, so 1/10,000th of the way there. So that's going to give us a new value of our A, and here's our new value of B. And so for the next row in Excel, our new intercept is simply equal to whatever we just calculated. Our new slope is equal to whatever we just calculated. And then thanks to the magic of Excel, we can just go fill down. And so by the end of it, we have our new value for A and our new value for B at the end of one mini batch. So that's it, right? And I guess the other thing that good people do when they're doing deep learning is that they check their derivatives. So we can also do that in Excel, finite differencing. So finite differencing simply means that we say, how much would our prediction change by if we changed our intercept by a tiny bit? So here it is. Here is take our intercept, add 0.01 to it, and see how much our prediction would change by. And do the same for A. Change that by 0.01, see how much that would change by. And that gives us a estimate of each of those two derivatives. So you can hear, my finite differencing estimate is 1202. My actual estimate was 1204. Okay, that looks good. So this is like everything that you would do in your Theano or Cafe or whatever. We've got the derivative calculations, we've got the backprop using the chain rule, we've got the finite differencing check that our derivatives are correct, and it's one line of Excel. So the purpose of this really is to say, whether you like Excel or not, it's like we can do, you know, one entire epoch in one line of Excel with no coding and nothing but, I think we've got plus and minus and divide and times, and that's it. So this is not rocket science. And so what would we do next? Well, we'd basically say, well, here's the intercept and the slope at the end of one mini batch. So to do another mini batch, let's take this, we'll copy it, and we'll paste it here to the intercept and slope. Okay, so I've just replaced the intercept and slope starting point with what we just calculated, and this now has just automatically calculated another mini batch. And so we could just keep copying and pasting and copying and pasting. And of course, we don't have to do that by hand. We can record a macro, which I have done. So here's my macro. Copy the last slope and paste it into the new slope. Copy the last constant, paste it into the new constant. And also, of course, what we should do as good deep learning people is we should visualize our learning. So we also have a graph. So each time it's going to take the RMSE and also paste the RMSE as well. So let's do 10 steps. Let's just do 5 steps. So if I do I equals 1 to 5, do one of these steps. Copy, paste, copy, paste, copy, paste. So we'll go run. Okay, done. So here is my first 5 points, and here is my error by epoch. And interestingly, you can see that it's actually decreasing at a linear rate, which is pretty interesting. And we've got the RMSE down. In step 1, it went from 150 to 104. From step 2, it's gone from 104 to slightly less than 104, slightly less, slightly less. It's going very, very slowly. So what would we do to fix that? We would maybe increase the learning rate. So let's try increasing the learning rate. Uh-oh, what just happened? So one nice thing about using Excel for this is that we can fiddle around and see what's going on. So what just happened was that we were basically saying, here's our data points we're trying to hit, right? And basically we've kind of found this function that if we increase or decrease the value, let's say, of A, this is A, this is our error, then basically we've tried to say, hey, there's some kind of shape here, and we started moving it kind of closer and closer and closer to the middle. But then when we made the learning rate too high, we actually jump over to the other side, which caused us to jump to the other side, which caused us to go crazy, right? So we can see why there's a balance between getting the learning rate high versus low. So let's put it back to where it was. So we can see at this rate, the error is going to take a very, very long time to get to 0. It's going down by like 0.2 each time. So how do we fix that? Well, if we look at these derivatives, you can see that the derivative with respect to B, this is just the sum of the squared of the derivatives on average. So the derivative with respect to B is pretty low compared to A. So maybe we should do something to make it so that those two are more aligned with each other. So those two are basically that the learning rate is different for those two different variables. Who's heard of Adagrad? So Adagrad's one of the most popular tweaks to stochastic gradient descent of the last year or two. Basically, all that is I've done it in Excel. This is exactly the same sheet as the last sheet. But what we're going to do is we're going to say, here's our sum of squared of gradients. And rather than have a single learning rate, each of A and B is going to have a different learning rate. And the learning rate is going to be equal to the overall learning rate divided by the sum of the squared of the derivatives. So in other words, each of my two variables' learning rates can now go at different speeds. So this treats this exactly the same as the last sheet, except for that one difference. So you can see I've got an entirety of one division being added in here. The cool thing about that is that we can increase our learning rate a lot. So I've increased it from 1/10,000th to 2. So we would expect to see things go much faster. So let's see what happens if we go to Algebra. And this is, as you can see, it's exactly the same. The only difference is that I'm also copying the gradient across at the end of each mini batch. So each mini batch will use my new per variable learning rates. So let's try that. Reset. And let's run 5 steps again. Last time, I think it got to like 104.3 was our RMSE. And this time, it's got to 71. So that one tweak of having per variable learning rates, which is just equal to the learning rate divided by the average derivative, has made a huge difference. So maybe if we run this another 5 steps, let's see what happens. Okay, we have a problem again. So as we got closer and closer to the bottom, things started getting flatter and flatter, and so it got to the point where it was very easy to accidentally kind of overstep. And as soon as that happened once, you can see what happens to the derivatives. It makes you worse and worse and worse. So this shows us why being very careful of learning rates is important. So in this case, what I would probably do is I would say, all right, let's run. We know that we can run for 5 steps without a problem. And maybe then we need to decrease our learning rate maybe by half. And then now maybe we can run another 3 steps. Yeah, looking good. Try running another 2 steps. Yeah, looking good. So we kind of got our RMSE down to 39 now. That's not bad. But this is like how many people here kind of implement deep learning or use deep learning, train algorithms day to day? Oh, not very many. That's interesting. So you'll find that the vast majority of people who are doing this is how they do deep learning. They basically run things for a while. When their learning rate goes crazy, they go back, they tweak it at some point. This even has a name. It's called a learning rate schedule. And it's, to me, we can see from using Excel that that's kind of insane. So I'm going to propose something which, what do you call this again, Diogo? Time warping or something? Diogo, this is like my Excel thing, and Diogo had to give it a name. Because in deep learning, one of the rules is like every stupid little tweak has to have a name that makes it sound really impressive. What I thought was basically, well, let's copy the same worksheet again, but maybe each time we notice something going wrong, we'll automatically decrease the learning rate. And what does something going wrong mean? Well, as I just watched the previous sheet, I noticed that when the numerical stability, or when the kind of numbers went crazy, it happened when the average derivative increased by a lot. It more than doubled. So what I did was I took my highly sophisticated VB macro and I added a little if statement that said, if the average derivative has more than doubled in this mini batch, then halve the learning rate. So this is exactly the same as the previous sheet with this one additional change. So let's see what that does. So we'll reset. And let's try running this now. So start with an RMSE of 308. And this time I'm going to run 10 steps without checking anything, without changing anything, and hopefully it's going to automatically fix itself. Let's see what happens. Not bad. So we've now got down to an RMSE, wake up, of 11. So and this worksheet took me, I don't know, half an hour to write. So far we've kind of reinvented Adagrad. We've invented a new approach to automatic learning rate annealing. And you can see in Excel, we've got to a point where our optimization running on top of our linear algebra is getting our error rate nearly perfect. In fact, if we run it for another, let's just run it for another 3 cycles and see what happens. Come on, wake up. There we go, down to 2. So I won't run you through the next 3, but I've got 3 more sheets, so maybe I'll put this on the internet so you can have a look at it. I tried adding momentum, which is another very popular tweak. I guess Adagrad and momentum are the 2 most popular tweaks. Momentum is simply to say, hey, last time I increased my variable, my weight by this amount, maybe the next time I should continue going in the same direction. So my entire change to add momentum was to add that, which is basically say, take the last change and multiply it by something, in this case I said 0.5, and add it to the next change. So you can try adding momentum. And then I tried adding both momentum and Adagrad together. And just for fun, I'll show you how well that works. So here's my both. Let's reset. And I also tried something else interesting here, which is I said, for the first 5 steps, let's not use Adagrad. The idea being that we'll take 5 steps to kind of get to a reasonable area of the function, and then for the next 15 steps, we will use Adagrad. It was just something I kind of thought, yeah, that probably makes sense, because when you start training a model, it's always actually a good idea to realize when you start training deep learning, your first few epochs will look kind of qualitatively different as you optimize them, because you're in kind of a really crappy part of the function space. So the first few epochs basically get you into a vaguely sane part of the function space. So again, I've kind of, this is now my entire Visual Basic macro. So let's see how well that goes. Run. Okay, so you see it zipping along. Here's my slope and my intercept changing. And you can see here, I'm not even using learning rate annealing, right? So by basically just making sure that my initial learning rate was stable, I didn't even have to use that learning rate annealing. And I'm now, without even worrying about learning rate annealing, we've got down to RMSE of 1 in 20 epochs. And then finally, let's do it all. So this one has Adagrad, learning rate annealing, whatever the hell we called it, time warp, something. And let's just see how well that goes. So if we put it all together, here is my all. Reset. So as you can see, it's not exactly complex. We're now up to like 10 lines of code. So let's try running just 8 epochs. So now in just 8 epochs, which is half the number we had before, pick up, go down to an RMSE of 6. So I think a few messages here. One is if you're playing with this stuff, keep it simple. Make sure you can visualize what's going on, and turn my Slack off, obviously. And furthermore, recognize that little tweaks to your algorithm change how fast you can learn things by many orders of magnitude. So if you went back to our first sheet, it would have taken like 6,000 epochs to get to this point. With some of these tweaks, I'm down to 8 epochs. And this is actually what we find, so in Lytic, when we're training these algorithms, these minor kind of tweaks mean that something that used to take weeks suddenly takes seconds. When we started doing CT scans, it took, I think it was like 10 days to train a single CT, and we're now down to 0.02 seconds. So a lot of people talk about how many GPUs they've got and their distributed, deep learning, whatever. We're still at a point where kind of the level of knowledge, academic knowledge about how to do deep learning is still at the pace where people are finding order of magnitude improvements, every few months. And so the idea of spending a lot of time distributing something across 100 GPUs compared to spending a few hours figuring out a slightly better algorithm improvement, at least at Lytic, we very much would focus on the algorithm improvements. In fact, If you have 100 GPUs, all of your engineering work is going to take a lot longer because you're thinking about all this distributed computation stuff. And furthermore, you're going to get lazy, right? You're not going to think about how do I do it in 0.02 seconds. You're going to be like, hey, I've got 100 GPUs. I better use them. So that's kind of my little starting, like, deep learning's actually, pretty simple. The only step I missed there was I had my linear algebra piece, which was the y equals ax plus b thing. The only difference we do when we deep learning is we stack these things together, and between each stack we add an additional line which basically says if this is less than 0, then set it to 0. If it's greater than or equal to 0, then we'll leave it as it is. And so that basically adds a nonlinearity which looks like that. And so if you stack these nonlinearities on top of each other, this thing here, I told you everything's got to have a fancy name. This thing here is called a rectified linear unit, or ReLU. So don't get distracted. I see now a lot of you guys haven't done much deep learning before, so don't get distracted by all these, new words that people invented. When you see ReLU, think, that, right? In other words, one more line of Excel. So then the next question I posed at the start was, what is it for? What can we do that we couldn't do before? Well, it turns out that stacking these things on top of each other and running an optimizer through them does something pretty neat, which is that, for example, if the thing that you were running the optimizer over, let's have a look, here we go, is 1.5 million images, and this is some great work from a couple of years ago from Matt Zeiler, who's now at Clarify, and at this point was at NYU. It turns out that if the thing that you're training against is images, the first set of weights, that first stack, automatically discovers simple geometric shapes like this. The second layer of weights automatically discovers slightly more complex geometric shapes like these. By the time you get to the third layer, it's discovered shapes like these kinds of patterns, which automatically match these kinds of images. By the time you get to the fifth layer, it's automatically discovered things which uniquely identify unicycle wheels, or things that uniquely identify bird and lizard eyeballs, for example. And so this incredibly simple Excel spreadsheet, when you run it on a GPU, which can handle 16 trillion operations per second, which is more than Excel, this is what it turns into. So very, very simple basics turn into very, very complex things. So what this lets us do, which we couldn't do before, is basically to learn things with unstructured data. So, I've been kind of doing stuff in machine learning for 20 years, and during nearly all of that time, we had to work with things that kind of looked like CSV files or spreadsheets, things where we had rows and columns, and that was what we kind of run our random forest on, or our regularized logistic regression, or whatever. With deep learning, though, we can take any kind of data and automatically build these kinds of incredibly rich features just using that training approach that we just saw in Excel, which means that we can now, which means that we can now do the same thing that we used to do with structured data with things like images, natural language, or analytic. We do a lot of 3D, MRI and CT, audio. Some of you might saw that blog post a year or so ago from Sonda Dielerman looking at taking songs and automatically categorizing them using deep learning. Any kind of signal or time series. These are all things which until a couple of years ago, there really wasn't good ways to compute with them. With deep learning, we now can. So, if you guys are thinking about doing a PhD, starting a company, or joining a company, the question you should be asking is, what are the areas in the world which use these things to make a difference? So, for example, doctors look at all of these things to decide how to treat you to try to keep you alive. So in other words, if you give doctors access to these tools, they could save millions of lives and avoid millions of unnecessary treatments. So there's an example. Another example, anybody in intelligence searching for troop movements on the ground is basically looking at that and that. So why not automate it for them? Anybody trying to figure out when their drill in fracking or whatever is about to die is basically looking at a time series signal and doing detection on that. So you can replace that with deep learning, et cetera, et cetera. You know, so sometimes I hear about people who tell me that they've created a deep learning company. You know what that reminds me of? In the early 90s, everybody told me that they were creating an internet company. It's like, what the fuck's an internet company? An internet company is the same as a deep learning company. It's mistaking the tool for the thing you use it for. So like, you know, Amazon is kind of internet for books and then after that, internet for shopping. You know, Google is internet for search. So on and so forth. So internet for X, you know, anybody using the internet in the early 90s could tell everything was going to get on the internet. I think everybody probably here can tell that everything is going to use deep learning. So what are you going to do with it? Deep learning for what? You know, if the answer is I'm building a deep learning company, just recognize you're building the same kind of commoditizable foundation that an internet service provider was in the early 90s. You're building something that's basically going to look the same for everybody. Somebody will win, and the person who wins will become, you know, the AOL or whatever of its time. And in fact, you're going to hear today from possibly the one who will be that AOL, which is Nirvana, because they're actually literally building hardware specialized for this purpose. And so unless you're like Nirvana, you have neuroscientists and electrical engineers and like you're going to build a whole new hardware platform, you know, don't try and be a deep learning company. Think about, there's all these things that no one's ever been able to do before. So what are you going to do? Deep learning for what? You know, if you're looking at doing a PhD, you know, deep learning for what? Deep learning for medicine, deep learning for oil and gas, deep learning for finding terrorists. I don't know. The final thing I'll mention before I wrap up is as you solve your, you know, hopefully genuinely important, impactful problem using deep learning, the current state of the tools is shit, as you all know, right? The current state of the tools is, you know, they all require code. What percentage of the world can code? The percentage of the developed world that can code is under 1%, right? So if you build a deep learning tool to help you solve your problem with deep learning and it requires code, then you've just basically said to 99% of the world, I'm not interested in helping you. Almost every deep learning tool today requires manual tuning, like that learning rate schedule that I showed you, or setting all kinds of parameters or so forth. Why spend a lot of time trying to get an extra 0.1% performance rather than try to spend the same amount of time removing all of that manual tuning for your users and doing it automatically? So what have we got so far? We've got kind of parameter tuning. We've got code. Another one is none of the current generation have error bars. What's the point of giving somebody a prediction if you don't tell them how confident you are of that prediction? What are they meant to do with it? And again, these are all things we have solutions to, right? So Michael Jordan at Berkeley has a paper called Bag of Little Bootstraps. Which can take any black box algorithm and add error bars to it. How come nobody's done that for deep learning yet? You know, like everybody who wants to use deep learning needs this functionality in practice. You know, this parameter tuning, there are plenty of algorithms to automatically tune parameters. Why are they not automatically used every time you use one of these algorithms? As far as I know, NVIDIA is the only company which has even tried to build a good code-free deep learning toolkit. So I think, a lot of us have got distracted by, things like the ImageNet competition. It gets far, far, far too much press if somebody beats, that benchmark by 0.1%. But if somebody comes up with a way to let normal people use deep learning to solve important and impactful problems that previously were unsolvable, no one hears about it. But don't worry about that, because if that's you and no one's hearing about it, you're still going to make billions of dollars, right? Like the internet companies where people did internet for X, they're the people that made billions of dollars. They weren't necessarily getting a whole lot of press or whatever for inventing a faster TCP stack, right? But they were the ones that actually impacted people's lives, and therefore they were the ones that made a difference and made a lot of money. My final suggestion for if you're building your own deep learning tools or working on others is that it's not enough just to show a prediction, you also have to show why. So for example, when we say to a radiologist, we think this is a malignant tumor, that's not enough. Why is it a malignant tumor? If there's another radiologist telling them that, they would ask them that question, so naturally they ask our algorithms that question. And the great thing about deep learning is that we can show them. We can say, well, here's this tumor I'm looking at for you. In deep learning space, here are the 5 most similar, right? And here is what turned out to be the result of the biopsies done on those. And then a radiologist can look at that evidence and say, oh, I see. I see why these are similar. I see now that this actually has some of the same, particular texture details as some of these tumors, and I can see that in all of those cases it turned out to be malignant. So that's great evidence, right? So you don't need to go in and show them the 600 million weights. You can use deep learning to show people evidence and examples. And again, if you can't do this, then I think the application of your tool is going to be very limited because you're asking people just to trust it. Okay, so that's my starting point. So for the rest of today, you're going to learn about how to do deep learning. What I hopefully have shown you is that deep learning basically is pretty simple. It's also incredibly powerful. It lets us solve things that were previously unsolvable. And so thinking about what you want to solve is a really good step. So I've gone 5 minutes over time, so maybe I'll spend 2 minutes if anybody's got questions. Otherwise, come see me. I'll be here all day. And of course, also, if you want to use deep learning to save lives and also make a lot of money, come see me about working at Analytic, because it's really fun. And there's quite a few Analytic people here who can tell you the same thing. Yes, ma'am? There is no unsupervised. People who try to convince you otherwise are tricking you, because what did they actually do? It's like, look over here at the unsupervised model, which I'm training with the supervised thing. So this is actually it's a great question. This is actually the stuff that makes a difference. This is like when people compute with deep learning, the same way that today we compute with code, these are the things that make a difference, right? So like, what are the kinds of things we spend time on at Analytic? We spend time on things like, I have a whole bunch of data, MRIs, of which we only know for this little group which ones had malignant tumors. So what do we do with all the rest, right? Traditionally, this is what people would call unsupervised learning. But if you look at every example of unsupervised learning, you just invent a supervised problem to solve. So for example, the classic case is the so-called autoencoder. So with an autoencoder, you basically say the goal of the supervised learning is to recreate the original image, but with a bottleneck layer. In other words, a layer in which there are less neurons than the size of the original image. So you've turned it into a supervised problem, and the supervised problem is recreate your input. There are other cases called Siamese networks, which basically create, again, kind of arbitrary supervised problems, which is figure out whether these two images are images of the same thing or not. Another example was the classic word-to-vec stuff that Google did. where the problem that they solved was they took 100 million 11 word long strings from books. They made a copy of them, and in the copy they replaced the middle word of the 11 with a random word. And then the supervised problem was try and predict which were the original sentences, which were the randomized sentences. So the rule of thumb is come up with as useful or semantically useful a kind of fake problem to solve as you can. If you do the autoencoder one, you're going to end up with a neural network which has all kinds of features you don't care about. It's going to figure out how to exactly replicate the background when you don't care about the background. So basically, for unsupervised learning, come up with an arbitrary problem to solve that is has as much semantic similarity to what you're going to be using it for as you can. So yeah, that's the second area that we spend a lot of time on is transfer learning. So with transfer learning, it's basically saying, you know what, this is a MRI of the brain, but we've already done 100,000 MRIs of the lung. How do we take the stuff we learned about the lung and use it for the brain? Or you can do similar things with, hey, we've already done English speech recognition, how do we do Chinese? So this is this whole area of transfer learning again, which is like super powerful, because if you can do that effectively, then you can basically turn all these kind of unlabeled problems into partially labeled problems. It would mean that every time we try to look at a disease for which we have very little data, we can use all of the data that we have about kind of similar diseases to help us, for instance. So yeah, transfer learning is another big area. Yeah, so overfitting is a largely solved problem now, which is basically, it's very similar to the way random forests solve the overfitting problem for structured learning. Random forests solved that problem by creating lots and lots of decision trees, all of which were like slightly randomly bad. The main thing that's happening in deep learning is each time you train in your network, you randomly remove half the neurons. And that basically enforces that none of them are going to overfit. So that's called dropout. And it turns out that there's strong connections between that and just actually taking your original input data and adding noise to it. So that's another thing you can do, is add noise to your inputs. Things like that, can basically, you can avoid overfitting. Look at your validation set. If you are overfitting, you can just increase the amount of dropout or increase the amount of noise until your validation set's working well. Last one.
A lot of people talk about that.
So the thing that's going to make it useful in deep learning is if you're able to use unstructured data that previously was not really amenable to analysis. All of the experience in Kaggle competitions has shown us that the winners consistently have found that adding kind of metadata or doing hand engineering of the features is not at all useful. And we've kind of found the same thing in analytic with our medical data. So generally speaking, it's just take the raw data, take the images or take the audio signals in their raw form. At Baidu, for example, their Chinese speech recognition now, it's just the input data is the waveform, The important thing is like what you correlate it against, with the dependent variable, or in medical speak, the ground truth, If we try to use the radiology report as the data we try to match, then we're going to make all the same mistakes that a radiologist made. If, on the other hand, we manage to get hold of the actual biopsy results, then we can make sure that we train it to be better than a radiologist because it's finding the truth. So Generally I find it's not so much the input data, which is where you have to spend a lot of thinking. It's like keep that as raw and simple as possible. It's more like what's the truth data is the thing that you need to be careful about. All right. Well, thank you so much, everybody, and thanks for your time, and hope to see you around the rest of the day.